way back in time and way lower temperature firing that Matt did. What I'm looking at is a Upper Paleolithic site in South China, in Yuchenyang, where I'm using FTIR to estimate firing temperatures and use of fires and cooking practices. Yuchenyang is a cave site in a karstic environment in South China in Hunan province. That was the wrong one. Right here. This site was excavated several times. What makes it famous alongside the site of Sernandong is the fact that a chopping tool technology, so a rough, lower to middle Paleolithic looking stone tool technology was found alongside pottery vessels and rice husks and phytoliths. So for quite some time, these two sites were interpreted as Neolithic sites with a problematic stratigraphy. In 2004-2005, Yuchenyang was re-excavated by a Sino-American team that took samples, radiocarbon samples, and micromorphological samples to really understand the chronology of the cave and see if the stratigraphy was really disturbed as once thought. What we found out is that the cave site actually is, well, the human habitation of the site is dated to the last glacial maximum, to the late Pleistocene, early Holocene. So the glacial maximum is between 26 and 24, depending where you are in the world, 1,000 years ago. It goes up until 14,000 years ago. And this is a time of global glaciation. However, in China, we found out that the monsoon system that still today causes the Eastern Asian environment to be different from what we can see in the Western world was already in place during the Pleistocene. So what you see here are the three arrows, white arrows, are the three main monsoon systems. The winter monsoon that from Siberia in the winter brings in cold weather and makes Beijing really, really cold. And the summer monsoon, the Indian summer monsoon, that makes Southeast Asia and South China considered almost tropical, subtropical environment. And the same summer monsoon coming from the east. The small letters and numbers that you see are the lake course, marine course, and speleothems that were sampled to reconstruct this paleo environment and to find out that, in fact, the monsoon system was already in place. Why is this important? It's because during the last glacial maximum, elsewhere in the world, the glacial caps, both glacial caps expand, and human beings, animals, and plants are pushed southward. So you won't find humans living above the 41st, so this is 40th north. Anything above that is considered almost unlivable for human beings, so steppe and tundra just shifts down the globe or up if you're south. However, this core area where our site is, because of the influence of the summer monsoon, remains a warm and wet environment, so almost a refugium for humans, plants, and animals. And this is very important to remember when we go and look at, oh, this is very pixelated, I apologize. When we go and look at stone tool industry, so in the Paleolithic, what we rely on a lot is stone tools to identify a site. And at this point, Homo sapiens in Europe is making blades and bladelet technologies, making atlatls. These are considered very upper Paleolithic tool technologies, and we see these moving eastwards. At about 40,000 years ago, they crossed the Altai Mounds right here, They arrive in China at 30,000 at the site of Shuidonggo, and they will then go towards Korea, South Korea. We don't have any sites in North Korea at 25, where we found them at 25. If you remember this line, dotted line here, which is where the two monsoon kind of meet, so where the influence of the northern monsoon ends up north, and where the southern, the summer monsoon reaches in the north. You see this line here is a line, a fictitious line of the boundary between this blade technology that we see coming in from Europe and a very lower Paleolithic, middle Paleolithic looking core and flake tool technology, which is very crude, worked on pebbles and has some flakes as well as tools. That is a Paleolithic up to the Holocene stone tool technology that we found in South China and Southeast Asia. So it's almost as if nothing changes in South China and Southeast Asia throughout the Pleistocene, all up until almost the Neolithic time. This was considered to be a sign of non-presence of Homo sapiens or of lower mental capability, so of non-Upper Paleolithic behavior, non-modern behavior in southern China. And this is important to remember because I will go back to it. So at this site in Yuchenyang, what we have is this chopping tool technology. If you do stone tools, if you've seen stone tool and blades, this is very different. It's something very crude alongside this pottery, these pottery vessels. We also find here a few bone tools, but pretty much nothing else. So the absence of blades and bladelets lately has been interpreted as a possible fictitious absence. And so Ofer Bar Yosef here at Harvard, this is very sensitive, did an experiment using chopping tools and trying to make blade tools with organic material. And they found out that actually you can use chopping tools to prep and sharpen. I'm just going to use this and sharpen a piece of bamboo to the point that it actually cuts through flesh. So they're proposing that in reality, what we have is not an absence of blade tools and of Upper Paleolithic tool technology, but just a different way of making tools here. The other part of the record, archaeological record of Serendong, is the zooarchaeological record, where we have several species from smaller mammals, rodents, rabbits, a lot of birds, especially water birds, and fish. We are on a alluvial plain, so that's pretty normal. But we also have a preferential butchering and transportation of cervids. In particular, we see that what humans are bringing in the cave are epiphyses, so the ends of the long bones and the vertebrae of the cervids. So this was interpreted as a preferential transportation for bone marrow extraction. In fact, the bones are crushed, so that you can extract the marrow, which has a lot of nutrients in it. There is the possibility that the processing of the bone was also used to extract bone grease. The difference is that bone marrow extraction is relatively easy to do. You just take a long bone, you crush it, and you just suck out the marrow. While bone grease, the bones need to be boiled. So you have to transport the water. You have to make a fire. You have to put the bones in the water, crush the bones, put them in the water, boil them for a while, scoop out the grease, and at that point you can use it. But it takes about 3 hours to extract 30 grams of bone grease. So it's a I swear. I don't know where I'm going anymore. You're seeing the entire thing. So it takes about 3 hours to extract 30 grams. And this is a very upper Paleolithic behavior. It's something that we don't see in the Middle Paleolithic or in the Lower Paleolithic, so while bone marrow extraction we see it very early on in the record. So this distinction is very important. Our zooarchaeologists weren't confident enough with what they found to say, yes, for sure, there is bone grease extraction. So this is what the cave looks like. I'm sure I'm not touching it. So this is what the cave looks like. It's about 25 meters across. What we excavated are this large square T1 that we divide in 1 by 1s, T10 to T13 and T4 and T5. The rest of the squares were covered in ebullition, roof vault, like you see here. Our radiocarbon dates were taken from profiles, and as you see out the radiocarbon dates on both sides and in the middle increase with the increasing of depth. So from the radiocarbon date point of view, there is no problem with the stratigraphy. So to make sure that that was true, we also took micromorphological samples to check the stratigraphy, if we had any bioturbation that was consistent, that was big enough to move the pieces that we were, the bone and the charcoal that we collected. Another thing that we looked at was composition. So we noticed that the eastern part of the cave, T4 and T5 right here, were made up of clay and ash and some charcoal and bone, but they were all jumbled up together. So they were mixed and in a chaotic manner. While on this side, you can see here, we have these lenses of ash and red clay. They are concentrated mostly on the southern portion of the western side of the cave, and this is what they looked like in the field. So it's pretty much an Upper Paleolithic hearth, right? That's what it looks like. The micromorphology confirms that in the western side, everything is pretty much chaotically arranged. Even when you look at stuff that optically looks in situ, when you look at it under the microscope, you see that the clay aggregates pretty much everywhere. One thing that we noticed with the micromorphology is that there's a lot of clay. This clay is relatively, like, I did not touch it this time. It's relatively clean, as you can see, and we can definitely go on. It always is pretty much consistent, and you find it everywhere. Sometimes you actually find it concentrated in those clay lenses, and what it looks like is these aggregates are packed together. There's nothing else in there here, but in others there's actually maybe a piece of shell right here or some ash into here. And then we find ash lenses like this that are in situ, and we have long pseudomorph, planned pseudomorphs still intact that we can see. So this also tells us that although this is well cemented, taphonomically nothing really happened here. There's not a lot of diagenesis happening. So from all of this, I came up with a few research questions. First of all, where does all of this clay come from? So if this is, a cave is a sediment trap, so whatever gets in there, and it can come in through water or air, so wind blown, or through humans, so you can maybe walk in and have, like Dan was saying, you get stuff stuck on your shoes, you walk in and you lose it. Animals can do the same, or it can actually actively be brought in. So the question is where is it coming from, and how does it get here? It looks optically, it looks burned. Also, there's a lot of ash in here. So are the clays and the ash crystals, are they somehow related? Are these hearths used for something, and what temperatures are they reaching? So what I use as methodology is micromorphological analysis coupled with micro FTIR. I used transmitted mode for clays, and as a control sample, I used the bones that were in the slides to check if we had the same kind of temperature heating temperatures on the clays and the bones, or different, and what could that mean. I used germanium ATR for the bones. We tried also, just if you wanted to do bones, we also tried diamond, and the spectrum, you can still interpret it, but it's very dirty, it's very noisy, so germanium works much better with bone. Now we'll go into actually really what you look at through all of these. So to answer the question of where does the clay come from, we found out that there's no geological way, natural way for these clays to arrive in the caves. So no way that water would bring it in, especially in these amounts. It had to be brought in by humans, and the sheer amount of clay suggests that it was intentionally brought in by humans. Where were they taking it from? They could have either taken it from the cave system itself. This is a shelf that is inside the cave where some clay is being transported by dripping water that goes through the rock. But also, if you walk outside, this is the view right outside of the cave, and as you see, all of these soils are full of clay. This is a sample of this soil exposure, and it's pretty much all clay, and it looks exactly what those clays looked like in the cave. We also took samples of bricks from a local factory that uses local clays, and just as a compare sample, and it seems to be always consistent. The micro FTIR that we'll look at this afternoon looks like this, and the way that I use it, instead of having a KBR pellet that you put inside, I actually do it directly on slides, on my micromorphological slides, and this way you can control where you are. You can control where you are taking the sample, right? And so you can actually, you know what's around it, what the status of the matrix is. The downside is that sometimes it's not super clean, and that you only get partial spectrum, or spectra rather than the entire spectra that you saw, for example, with Matt. And I'll show you what this means, is that if this is a spectra for clays, right, I only see this portion right here. So what I can look at is only those main kaolinite peaks. And so as how Matt was saying before, the 3 peaks that I'm interested in out here are 3690, 3650, 3620. That are the 3 main kaolinite peaks that disappear with dehydroxylation of clays. And so, because this is the upper Paleolithic, I don't have to reach over 700 or 800 degrees, because a campfire doesn't usually reach over 800 degrees. So I'm only looking at what's below 700. And this Francesco Berna published in 2007 this paper that looks at these 3 peaks and how they disappear one by one, going up from 500 to 700. So you reach 400, they're still there. 500, they're starting to go away, and it's almost like they're getting erased one by one. The same thing. So I look at bone and with the germanium crystal, and the same problem. I get here the same problem, which is I only see part of the spectrum. So what I can look at are the phosphate peaks down here. And you can see, this is again from Berna, from an article from Francesco Berna. And what you can see is the appearance of this one phosphate peak at 330 that arrives at about 500 degrees. So anything below that, it's either non-heated or we just can't see it. And the appearance of a peak at 1096 in the apatite groups, which also appears at about 500 degrees. So this is what my samples look like. In the same slide, we can find clays that are not heated at all, clays that are partially heated, and clays that have no peaks at all in the 3690 to 3620 range. This is not that crazy. If you buried yourself underneath, just 10 centimeters underneath a campfire, you'd be totally safe. Actually, soil and clays are very good insulators, and so when you've built a campfire, the heat only penetrates down to about 10 to 20 centimeters. And so if we are looking at clay surfaces that are man-made on purpose to build fires on top, right? Just to have a fire on a clean surface, and we see this in the Upper Paleolithic record elsewhere in the world, from the United States to the Levant, that heat will penetrate only so much. So it's normal that we see this. There's also the rehydroxylation problem that, I'm sorry, I don't know your name. Oh. You mentioned rehydroxylation earlier. So there's also that problem, the fact that these clays might have been rehydroxylized, but the fact that we have samples that are not, that don't have the peaks, it should tell us. I'll go on. So if we keep going, we see more samples of these clay surfaces that are pretty much clean, with these clay balls that are all stuck together, and the clays always look like this, right? The bone in the same samples associated with these surfaces, this peak, do you remember the peak of 1096 in the apatites? There is no peak. This is very clean, and this is actually, we took 4 different scans of the same bone just to make sure that it's consistent, and there is no peak. If we keep looking at bones, right here, this is clays and bones from 2 samples that were collected right beside pottery, the pottery vessel that you saw before, or the reconstruction, those pottery fragments. The clay looks heated, right? There's no peaks in that 96 range, but the bone, heated, but the bone doesn't look heated at all. I'll keep going. So what we're seeing in this cave is a high volume of ash. It's only ash. There's all of the sediments that we collected, basically only have combustion features in them. We also see a positive ratio between ash and charcoal. There's very little charcoal and a lot of way more ash. The clays are heated between 400 and 600 degrees, depending on those peaks that disappear, while the bone is either not heated at all or heated up to 100 degrees, right? It looks fairly clean. We have chopping tools, we have pottery vessels, and we have these clay surfaces. We have preferential transportation of marrow-rich and fat-rich bones, and we have the preferential fragmentation of the epiphyses of the long bones and of the vertebrae. So what I suggest is happening here is that not only humans are bringing in bones to be so that they can extract marrow, but what they're doing is also fragmenting these bones and boiling them, probably in the pottery vessels where we need to do residue analysis to be sure of that, to extract bone grease. And this is the proof that this is a very Upper Paleolithic environment that we're looking at. Although there are no Upper Paleolithic stone tools, the behavior that we're seeing is a very modern behavior. Not only a cooking and subsistence behavior, right? Both pottery and bone grease extraction are intensification of subsistence strategies, which means that something is making these people go through the trouble of keeping these fires for long periods of time, so oxygenating them, collecting all this fuel, making these fires and keeping them at a temperature that allows them to keep boiling these bones for hours at a time, to extract, what, 30 grams of marrow per 3 hours? So 10 grams an hour. And to do this, you have to remove a portion of your population from your everyday life, which means that those 3-4 people are not going out, they're not hunting, they're not gathering. That is what they're doing today and tomorrow probably. So something is pushing these people to do this. And in a place where environmentally everything seems rainbow and unicorns, right? It's warm, it's wet, everyone else in the rest of the world is freezing. And they're like, ah, la la la. But actually, something is happening. So not only we're seeing an Upper Paleolithic modern behavior in a cave where humans are using Middle and Lower Paleolithic chopping tools, but also we are looking at some kind of pressure that this population is going through that we still don't understand and we really need to look into. Unfortunately, when we have 2 caves, we are working on it. So with this, I would like to thank everybody for coming, and Arthur for helping me with the FTIR, and Tübingen University as well. We have lunch now. I think we have some time for questions, and then we can move to lunch, and then we do the last we'll do the last talk.
So we'll do the last talk at 1, and I'll shorten my tour of the center by a couple minutes, which will be fine.
You can secure it in different ways, plaster, just if there's a lot of clay, you can just take the chunk out and wrap it in toilet paper and tape and keep it together. The important thing is that you want this block to stay as intact as possible. Then we bring it back into the lab, we dry it, and then we impregnate it with resin so that it becomes this hard block that we can cut through it, and then we mount it on just regular glass slides, and you then grind it down, and you put it under the microscope, and you can look at composition, you can look at organization, etc. Most slides are covered, like slides that you work with in a lab. Most of the time, they will be covered on both sides with glass. But because we're doing FTIR, we leave one of the sides open. So if you want to do FTIR on sediments or soils, or even just petrographic, so ceramic slides, you want to leave one side uncovered so that you can use it, and not polished as well. Polishing it doesn't really change the FTIR all that much. It's just an extra step that you need to pay for.
What resin do you use to impregnate the specimen?
It's a unpromoted resin, polyester resin with MEK.
The catalyzer is methyl alpha ketone peroxide.
That one.
You can use promoted or unpromoted. Unpromoted works best. The only problem is it's a little harder to get than.
I have used boat resin in the field, and
Yeah.
it works just fine. You just need to play a little bit with the catalyzer, but it works. Especially if you're in a really hot environment and you're taking smaller samples, it doesn't.
And epoxy
make
works as
difference.
well. It's
Yeah,
just
epoxy works as well.
you need to dilute it more, and you need to be a little bit more careful with water around
Yes.
epoxy because it absorbs water as
Yeah.
it cures.
So just make sure that your sample is really, really dry. Otherwise, you're gonna get bubbles. You're gonna get if you use epoxy, it's gonna absorb it. So as I said before, the good thing about using the slides is that you can control exactly not only exactly where you're taking the sample, but what is around it. And you can analyze relatively small objects, or bones in this case, or clay aggregates. The downside is that you only, as I showed you before, see small spectra, right? The smaller parts of the wave numbers. That is the machine that we're going to use today, and that is what I've used for the analysis that I did. So when we look at clays, and we went through this a little bit with Matt, but I just put it in writing so that you guys can actually have it in front of you in black and white. So what happens to clays when we heat them is what we're looking at is the water, especially at the lower temperatures. So at 200, the clay that is not structurally bound with the water that is not structurally bound to the clay evaporates. In between 450 and 600. So 200 is those bricks that you would find in Chadahuye, for example, right? So Neolithic sites in the Levant made of bricks that are not necessarily burned or cooked in a kiln, but are just air dried. So what would happen to them is that the water is evaporating. If you put those bricks in a kiln and you heat them up in between 450 and 600 centigrades, what you're doing is removing that water that was structurally bounded to the clay molecules. And that is the process of dehydroxylation. So those OH that Matt was talking about, that OH group, the hydroxyl groups that Matt was talking about, that is exactly what we're looking at, is the absence of those. So those three peaks at 3690, 3650, and 3620, and the range of all three of them, disappear with that heating. And the glassy phase, the vitrification that Matt was talking about, appears at 950. And what happens to if you're firing a vessel at 500, 600, your vessel is still relatively porous. The vitrification makes those pores either disappear, the higher you go up, or reduce, right? And so you get in this glassy phase, low porosity and new crystallization structure. And again, this is what we are going to see today. So this is the complete spectra of clay, and so you can actually see that there are other groups apart from the hydroxyl group down here that you might want to look at, and you're actually going to probably see them with Matt downstairs because he's going to do KBR pellets with clays. And so you'll see that there's these peaks at 500, that 500 and 472, that shift or change. There's these peaks in this trough at 750 that change, but really Under the microscope, we don't see that. What we see is only this little box. And so we look at, again, 3690, 3650, and 3620. And as you see here, there's just, it can be just 3621 or 3697 in this case. But they're always those three peaks that are also, if you, in the literature, they might be called the main kaolinite peaks, or the main absorption peaks of kaolinite, instead of hydroxyl peaks. It just depends. What happens to bone under the microscope? Under heating, when exposed to heat, is a rearranging of the crystal structure. So Dan mentioned the word crystallinity index, and that is how the crystals in a bone are arranged and the strain that they can take. And that it was noticed that the lower the bone was heated, so from non-heated to 100, nothing, the more chaotic that crystallinity index was, the more you heat it, the more those crystals rearrange themselves in a ordered pattern. So what happens that you can see visually is that in between 25 degrees, so non-heated, to 250, a bone loses water, but also changes in the organic and mineral matrices. So that's the organic portion of the bone gets burnt, gets cooked, right, and evaporates and it gets burned. This is the point where you have char. So if you barbecue, that stuff that falls off, right, and just drips down, that's char. And actually in the archaeological record with FTIR, you can, with micromorphology, you can see it. And that also tells you that in that specific area, the fire wasn't hotter than 250, because if you look at 300 to 500 degrees, that char completely disappears. So all of the organic and mineral, the organic matter is completely gone at this point, and we get a mass loss because of that, up to 55% of mass loss of the bone, and then associated with this, there's the increase in the mean crystallinity index, and I can give you the reference for these and for other studies that have looked at